Alright, Calc 3 class, we are going to jump into triple integration now. So what is a triple integral? It's the same concept as a double integral, except now we got a third one on there. So when we look at a single piece that we use to come up with integration, this now remember we have ordered triples are the things that are going into some, three things go into a function and one thing comes out. So x, y, and z are going in. So within a region where we go up and down by these small changes, delta x, delta y, and delta z, we just pick a number. This little star means it's something that's within each one of these boxes that we use into the function. So we plug these into f, and that gives us our output. And it's like hypervolume. So we have 3 dimensions. Like when we had 2 dimensions, so we had a rectangular base, delta x, delta y, and then we went up by the function height. Well, now we got delta x, delta y, delta z, and we're going into the 4th dimension by the output of the function. So this is the old base. Instead of area, now it's volume, and it's being sent to the 4th dimension by the function. But the concept is still the same. How do we get the idea of the integral, the definite integral here? We sum these hypervolumes all together. So we're getting the hypervolume under, quote unquote, under the hypersurface of fxyz over these regions, and we get these boxes. But just the same concept, it's just extended into a dimension beyond our physical dimensions that we can see. But the math still works out the same. So just like before, the triple integral is defined what it's going to be. Now we're talking about over some volume. Okay, S is some surface in our 3-dimensional space, and this is a function that takes in 3 inputs and spits out a 4th-dimensional output. But it's the exact same concept as it was before. Alright, and then Fubini's theorem that we've seen before. If we got a rectangular region, the order of integration doesn't matter. So this is what this is saying, dx, dy, dz, but any permutation, and that means dy, dz, dx, dz, dx, dy, any order of these 3 that we can come up with is going to give us the same thing with our rectangular region. So quick example there would look like this. Alright, so we got this region. Notice we got x, y's, and z's in our function. This is our region S. This would give a volume. So notice that's why we have a dv here instead of dA like we've seen before. But 1 by 3 in the xy, or the x-axis, negative 1 by 2 in the y-axis, and 0 to 2 in the z direction. So again, if you're looking at our space, there's our x, y, z. So we're going from 1 to 3 for x. Sorry, 1 to 3 for x. X, that's usually what's coming out at you. Alright, and then we are going from negative 1 to 2 in the y direction. Alright, and then up to 2 in the z direction. Let's say that that's 2. Alright, so if we kind of made that box along the bottom, I'm doing with this a mouse, so forgive me if it's not perfect. Alright, and then up to 2 in the z direction. So it's just this rectangular box. Just think like a shoebox. This is where all the points live that we're going to send out into this function. And we're going to find that hypervolume underneath there. Again, you can think of that as color like we talked about before. But for all these points within this box, in this region, we're going to find the definite integral between these values in this and the 4th dimensional function's output. Alright, so the order of integration I set up doesn't matter here, but I'm going to set it up just dx, dy, dz, just alphabetically, but again, we could switch it around in any order we want to. I would, put this 0 in at the end if you have a 0, just because it just makes it easier on that last integral, but it won't matter. Now these are functions of x, so we're going to take the x's up by 1 power, but nothing else changes on the first one, right? So x cubed, x squared over 2, and then I'm plugging in 3 and 1 for these x's and subtracting. So when you do the math, that simplifies to 26y minus 4yz cubed. All right, so the x's are gone. So all we have left is y and z. That should always be the case. All right, and then when I integrate again, this is with respect to y, so I'm going to get a 13y squared minus a 2y squared z cubed. And then I'm plugging in 2 and 1 for y and subtracting. Sorry, 2 and negative 1 and subtracting. And I'm going to get that left with z. And then again, with z, because the bottom number is 0, I'm just going to plug in this 2 everywhere into the antiderivative. I don't want to worry about plugging in the zeros because everything's going to go away. And I'm left with 54. And that's what I would get if I changed the order of integration and did like z first, then y, then x, or anything. I would have gotten 54 no matter what. Because that is the hypervolume underneath the hypersurface over that rectangular solid. Alright, triple integrals have all the properties of double integrals, meaning like if we multiply the function by a constant, we multiply the hypervolume by a constant. We get the same thing. And the sum difference property that we've seen, all that stuff breaks apart. Alright, this disjoint region property, this is like if we had to break apart a region, because like when we're integrating, it has two different definitions, meaning like what's the upper function, what's the lower function, or if there's like an asymptote or a discontinuity. This is the same thing in the fourth dimensional world. This is just the union of two subregions, and this is splitting it apart over those subregions. So we could, in like calculus 1 with single variable integration, it's like this is the area to the left of the asymptote, this is the area to the right of the asymptote, and so we're splitting it up and adding those two areas together. It's just again a higher level version of that same property. Alright, when we set up these integrals, it's very important that we understand the order. So we have these two integrals right here, and I want you to see that when we send it down to the xy plane, like where the integrals either start or stop or intersect, notice right here what we have in the xy plane. We have y is dependent upon x. So for this x to this x, there's an upper y and a lower y, just like we saw before. For this z and this z, they're to function by, the outputs of these z's are determined by x and y. The outputs of these regions here that were defined, that these two regions above and below are defined by, are determined by, the y values are determined by x. And then finally x has a lower bound and upper bound. So it's extending the same concept that we saw before, one more dimension. So before we said, alright, pick something in here, and now the y's depend on those x's. How far off the x-axis we go, the y-coordinate, is dependent upon which x we're at. How far we go above these points is dependent upon which x we're at. But now that we've created that region where the x's and y's live, how far up we go is dependent upon the point. So for the upper z, it's this function of two variables. For the lower z, it's this function of two variables. And so that's the idea here, is our order of integration, we're going to start off with just constants on the outermost limits integration. And then we're going to have a function of this outer variable. So y is a function of x. And then here we're going to have a function of the two variables that we've already used so far. We've used x, we used y, so this is going to be a function of x and y. It's very important that we understand when we set these up, we have to set them up in two variables, one variable, constants. Alright, two variables, one constant. And we can never go back. Like So here's z, x, and y. And then if I come back here, y, it has to be defined by x. It cannot be defined by z. It can't be, this is dependent upon z, this is dependent upon z, because I've already gotten rid of my z's in the notation. So we have to work progressively towards constants. We have to remove variables every time we go down when we do this. Okay, and that's what this slide is talking about. Make sure you always are going from two variables to one variable to constants when you set up your integration. Okay, so find the volume of a solid that's bounded below by this surface and above by this surface. So this is like a, if you look at our notation, this is a 1 to 3 with the coefficients of x and y. This is elliptical in x and y, and this is like a paraboloid. And these things will, this one will be bending upward as we make our way away from the origin. This will be falling downward because we're subtracting it from 6. This is a concept very similar to what we did when we found area using double integration, because we said double integration, oh, that gives us volume underneath the surface. But if we made the integrand 1, that gave us area, because the area and the volume would be equal if that's the case. Well, we do the same thing here, and then we'll just make this our upper z and this our lower z when we set up this this triple integral. Okay, so this is a picture of what it looks like. There's our paraboloid opening downward. This is our elliptical paraboloid opening upward. And if you look right here, this is the intersection of those two. Those two intersect along this region right here. So if you look at what I've done here is I've just set the upper function equal to the lower function, and then we'll get the equation of where these things intersect. So notice if I move this x squared to the other side, and move this y squared to the other side, and then move this 2 over to this side, I'm going to get a 4 equals, this x squared joins that x squared, makes a 2x squared. This y squared joins that 3y squared and makes a 4y squared. And then just dividing both sides by 4 to get the standard form, we get x squared over 2 plus y squared over 1, or just y squared. And that would be an ellipse. So these things intersect an ellipse, and there's the ellipse that we get down below. And the ellipse, if you notice what they've got it set to, this y is equal to the square root of 1 minus x squared. That's just solving this for y. So y squared over 1, that's y squared. If I subtract x squared over 2 from both sides, and then take the square root, I'll get plus the square root minus the square root. So once again, we get that plus minus square root look when we have these round bases like we've talked about before. And that's a way that we can describe the region where these things live. That's the region of intersection, and so all the points above and below are going to be on the interior of that. Okay, so we have that ellipse shape. Our values for x, because y is dependent upon x, that means x is going to have our constants. The values of x on that thing are going to run between square root of 2 and the negative square root of 2 on one end to the other. So like this end down here would be the negative square root of 2, this end would be the positive square root of 2. And I know that because of the denominator. The denominator is 2. So that's, again, that's how we know that it's going to be negative square root of 2, positive square root of 2, when we had that standard form of the ellipse. So there's going to be our setup. We're going to take these are our outer limits of integration. These are the ones on the middle, and then the upper ones are going to be the two functions themselves, the upper one minus the lower one. Alright, and there's our limits of integration all the way through here. Okay, and we're doing 1 dz dy dx, again, because this will give us the volume. It's a hypervolume, again, technically with a 1 there, but because of the fact that the integrand is 1, the hypervolume and the volume are equivalent. Alright, so the first thing I'm going to do is integrate and plug this in, so I get a z, and then I plug this in minus plugging this in. So 6, this is just that ellipse that we saw, the intersection. But I plug in this minus this, I subtract the 2, this minus this, I get the negative 2x, this minus this, I get the negative 4y. So that's where all this new integrand is coming from. It's just integrating with respect to z. There are no z's, it's just 1. So I'd get z, and then I plug these things in for z. Remember, these were z's. Alright, now integrating this with respect to y. So I get this stuff times both of these things, just get a y, and then this gets a y cubed over 3. So I'll plug in these radicals, and once again we're plugging in radicals in place of y. So it gets messy. You can simplify this when you plug all these things in. You end up with this integrand, and then because I'm integrating with respect to x, and this is underneath a radical following a minus sign, I would use square root of 2 sine theta, if you remember that from trig substitution. Radical, subtraction, perfect square. The variable is behind the minus sign, so that's a sine trig substitution. And then you do the work, you get a power of cosine, and when we have those powers of cosine, we use that power reducing formula for cosine, and so that ends up giving us this number. And then this next one just shows that we would have done it in a different order. We would have still got the same thing. So now we reverse the x and y. Alright. Our middle integrand, instead of having the x squared over 2, we end up with the 2 minus 2y squared on the inside. We still get the same thing. No matter which way we do it, you can set it up that way and show that it's equal. Now, because of all these x squareds, y squareds that show up everywhere, this is another one that would be made easier if we switch to polar, and that's what we're going to get into the next section.